So today's video is on isomerisation. And so first we're going to look at the types of isomerisation. And the two main types are stereo and structural. And included in these, stereoisomisation, there is geometric and there is optical. But optical will be more focused in year 13, so we won't be looking at that today. And in structural, there is functional group, there is chain, and there is position. And we'll be looking about what these mean now. So first, structural isomerisation as a whole can be defined as isomers having the same molecular formula, but a different structural formula. And molecular formula is the number and type of atoms in a molecule. And the structural formula is how these atoms are bonded together in space. So if you have a look at our example here, we have our molecular formula, which is showing you what atoms and the number of atoms. And our structural formula is showing us how these atoms are bonded together, which the molecular formula doesn't tell us. And so the first type of structural isomer are chain isomers. And chain isomers is when you have 4 or more carbons in your carbon chain, you can have multiple arrangements. And this means that all of these chain isomers have the same molecular formula, but the carbon chain is bonded in a different way. So if you have a look at our example here, in this pentane, we have all of our carbons bonded together in a straight chain. And in this example, you see that we only have 4 of our carbons bonded in a straight chain and 1 of them bonded off as a branch, and here we have 2 branches. But if you count up all the carbons and all the hydrogens in all 3 of these isomers, you'll get the same molecular formula, the same number and type of atom, even though they are bonded differently. And these are chain isomers because it's the carbon chain that is bonded in a different way. And then we have position isomers, which is another type of structural isomer. And position isomers are when the functional group is bonded in different positions about the molecule. And this means that these molecules have the same molecular formula, it's just the functional group's in a different position. And just to reiterate, a functional group is a group of atoms that determines how the molecule reacts. So in our example here, we have our OH group bonded to this carbon, and in this molecule we have our OH group bonded to the middle carbon. So even though they have the same molecular formula, the same number and type of atoms, they're bonded in a different way because the functional group is bonded to a different atom. And our last type of structural isomer is functional group isomers. And functional group isomers are isomers that have the same molecular formula but a different functional group. And this means that they belong to different homologous series. So if you can see here in our example, we have the same molecular formula in both of these molecules, the same number and type of atoms. But in this group, we have an ether functional group. And in this one, we have a hydroxyl, an alcohol functional group. And it is important to note that the only functional group isomers of alkenes are cycloalkanes. So if you can see here, we have a certain number of carbons and a certain number of hydrogens that make up our molecular formula, and the only functional group isomer and the only molecule that doesn't have the same functional group that has this same molecular formula are cycloalkanes. So this will have the same number of carbons and same number as hydrogens as this alkene, even though it doesn't have the double carbon bond, meaning it has a different functional group. And now we're moving on to stereoisomisation. And as a whole, this is isomers with the same structural formula, but a different displayed formula or arrangement in 3D space. So our structural formula, as before, is how the atoms are bonded together. And our displayed formula shows how all the bonds are arranged. So as you can see here, even though on both carbons in these molecules there are a hydrogen and a chlorine, so they have the same structural formula, how the atoms are bonded, so both of these atoms are bonded to this carbon in both of the molecules. Our displayed formula is different because the arrangement of the bonds is different. So in 3D space, this chlorine is over here, while on this molecule, the hydrogen is over here. And so the type of stereoisomisation we're going to be looking at is geometric. And geometric is having the same structural formula, so how the atoms are bonded, so which atoms they are bonded to, but it has a different arrangement in 3D space. And this can be classed into two categories. This can be cis or Z, where the higher priority groups are on the same side. So in this example, both of the chlorines are on this side of the molecule. And then we have trans or E, when the higher priority groups are on opposite sides of the molecule. So in this example, the chlorines are on opposite sides. And higher priority is just established by the atomic mass. So chlorine has a higher atomic mass than hydrogen, so the chlorines are the higher priority group, meaning that to be a cis, the chlorines will have to be on the same side because they have the higher priority, the higher atomic mass. And how do we get geometric isomers? Well, in single carbon bonds, there's a 360-degree rotation. So this means alkenes, for example, will not have, alkanes, for example, will not have geometric isomers because all rotations around the molecule will be interchangeable. So, for example, in this molecule here, this oxygen could be down here, for example, and this hydroxyl could be up here. But because there is a full rotation around this single carbon bond, it will be the same molecule because they'll be able to freely interchange around this bond. But there is limited rotation around a double carbon bond, meaning that the different orientations around the bond are actually different isomers because they are not interchangeable. So this molecule can never be this molecule because there is not 360-degree rotation around this bond. So this chlorine will never be over here when it rotates. And that means that these will be different isomers because they cannot interchange with each other. Whereas with this molecule, because the 360-degree rotation around the carbon bond, these different rotations will be interchangeable, so they're not geometric isomers.